Hi, Professor Herzon. How are you?
I'm good. How you doing, Caroline?
Doing all right.
I didn't see your email until this morning. Did you get an answer from the TAs?
We did, yeah. Thank you
Okay,
very
good.
much. I think we just originally we thought we had to do the arrangement for every single atom in that or every single stereo center, and then we realized we did not have to do that, which was good.
Yeah, no, you can just do the just do the new bond. Okay, good.
Yeah.
I'm glad that worked out.
Thank you very much.
All right, good morning. Hope everyone's doing well. Today's lecture is going to focus on conformations of cyclohexane and substituted cyclohexane. So I hope that you had a chance to watch the lecture from Friday and read the chapter, the relevant text in Loudon. Just to recap Friday's lecture, we talked about the strain energy of cycloalkanes, and we used this comparison of the heat of formation of each CH2 group as a way to make a head-to-head comparison of the strain energy in different rings, and then also for cyclohexane to straight chain alkanes. And essentially what we find is that on a per CH2 basis, the heats of formation of cyclohexane and hexane to heptane are identical. And so the conclusion then is that cyclohexane is an unstrained ring. It doesn't have any ring strain in it. And then we took a little bit more of a dive into the actual conformation of cyclohexane, and we said it's not actually a planar molecule. It doesn't sit as a ring, flat in your paper. It actually forms what we refer to as a chair. So I'm going to redraw that here. Okay. And what we said about the chair is that the hydrogens the hydrogens at each carbon have a discrete orientation that we refer to as an axial or equatorial position. So I'm going to pencil in all of the hydrogens here. Okay, and I'll box the axial ones in red. And circle the equatorial ones in blue. Okay. And so now I want to introduce this idea of a chair flip. Okay, and to introduce this, it's good to think about, let's think back to ethane for a second. And we said that ethane had two conformers that were of interest, the staggered and the eclipsed conformers. And we said that at room temperature, those conformers are rapidly interconverting, right? They're technically, they are stereoisomers. They're conformational isomers. They interconvert by easy facile bond rotation. And the reason they do that bond rotation is it's just a way for the molecule to give off energy, right? So these molecules have energy and the movement helps them to disperse it. Rings such as cyclohexane are subject to the same sort of principles. They have a finite amount of energy and they'd like to get rid of that energy by moving around. But because of the ring structure, you can't twist, just twist a single CC bond in cyclohexane, because obviously then you deviate it from this ideal chair geometry, and that would cost you energy. And so what happens is that in practice, there's what we call a chair inversion, okay? And in the chair inversion, all of the equatorial substituents become axial and vice versa. So let me number carbons so you can follow this. All right. And then I'm going to draw the chair flip product, okay? And to do this, I'm going to start at C1. That carbon is going to flip down, okay? And I'll build my chair from there. And let me number carbons here. Well, let me put in the hydrogens first. Okay, and I'll number the carbons so you can see where each one ended up. All right. And here's the key. Here's the important point is that let's look at the hydrogens that are attached to C1 up here, okay? If you imagine that I'm taking C1 and pulling it down, okay, to get it into this orientation in the bottom, I'm flipping that thing down. And so I'm not changing the configuration at the center, assuming, we could label the hydrogens and differentiate them. I'm not changing the relative positions. So I need to hold them constant. And so the boxed H that is axial is on top in the top structure here. Okay. That one still needs to stay above the equatorial hydrogen that I've circled. And so if you follow those down as I'm kind of pulling C1 down, the boxed one ends up here and the circled one is pointing down now in an axial orientation, okay? And that is true for every carbon atom. So everything that is axial in the top structure is now equatorial in the bottom. And everything that was equatorial in the top structure is now axial in the bottom. Okay, 2, 3, 4, 6, yeah. And so this is what we refer to as a chair flip. So okay, so all equatorial hydrogens in one conform move to the axial position in the other, and vice versa. Okay, And this is a mechanism by which cyclohexane gives off energy. It's like bond rotation or bond vibrations, bond bending. For cyclohexane, you do a chair flip. And so these chair flips are rapid at room temperature. The two chair conformers are interconverting. Okay. So the question then is, how do you get from one conformer to the other? And it's complicated. We're going to go through it in a second. You have sort of a hint of it here. If you follow C1, I've kind of like pulled C1 down and going to this bottom conformer. And if you look at C4, for example, that gets pushed up as I go into that conformer on the bottom, okay? And that's exactly what's going to happen. They're not going to move at the same time. They're going to move in individual steps. And, you know, these movements, of course, are continuous. You know, you bring that bond down, that carbon C1 down slowly, and the conformation changes incrementally. And so we can generate a potential energy surface for this chair interconversion. So let me go to the next slide. Okay. And what we're going to do is draw energy on the y-axis. Okay. I will start with one of my chairs, and let me let's see here. Okay, I'm going to start with the chair that is on the bottom on the left here. So we're going to go from that bottom conformer up to the one on top, okay? And over here on the right, I'll draw the chair flip. And if we number carbons as we had them before, this is C1. Now this is C1, this is C2, 3, 4, 5, 6, 2, 3, 4, 5, 6, okay? So what I'm going to show you is the path between these two conformers, okay? Because there's a lot that's changing. And so before we attempt to just draw it in these 2D diagrams, which, you know, are very inadequate, I want to show you a quick 1-minute video that I made in Spartan that shows this, and I'll post this to the let me see here. I don't want to lose my whiteboards. Probably gonna lose it. All right, let's see. I will post this to the website for you. So let me go. Right. Okay. Can everybody see the movie? See the model? All right, great. Yeah. So, okay. So on the left, I've got the cyclohexane, okay, as we've drawn it on the left hand of that energy diagram. The little dots, the red dots in the back of the image here correspond to the energy of the different. So each dot corresponds to a different intermediate in the chair inversion, and its orientation in the y-axis is its relative energy. So here, as I progress through the dots from left to right, I'm going up in energy and then down and then up again and then down, okay? And so the chair that I start with is the energy minimum. If I jump to the other end very quickly, let me see if I can do that. this is the chair on the other side. So if you look at take a moment to look at your potential energy surface diagram, we have the two chairs. That is what I'm showing you here. And then all the dots in between are how we get there. It's the path between the two. And so let me go back to the beginning and I'll play this video. And we're going to look at it a couple times. So just take your time. Okay, there you have it. So I'm going to play it again and I'm going to stop and sort of editorialize as we go through it. Okay. So here's chair conformer number 1 on the left side of your diagram. And what we're going to do is slowly move C1, so the carbon that's over here on the right. Can you guys see my pointer?
Yeah.
Yeah, okay. The carbon that's on the right, we're just going to incrementally move this up, okay? And, you know, the other carbons are going to twist and wiggle a little bit, especially the ones that are directly attached to it. So the one in front here and the one in back. But these 3 all the way on the left at this point are not changing all that much. So just sort of pay attention to what's happening on the right. And this guy's going to start to come up. Okay. Follow this proton here. So this one is equatorial. Look at its change in orientation. Do you see that? So I can stop it right there. And we can say that now this proton is almost vertical. It's not there yet, okay? But it looks like it's trending towards an axial orientation, and that is what's going to happen, all right? The other proton that was axial is now pointing much more closer to horizontal, and that one's going to occupy an equatorial position, okay? And so this maximum on the energy diagram right here, you know, the circle at the top, that's the one we're looking at. This is the maximum on the energy surface, so it's a transition state. And this transition state has a specific name, and that is called what's known as a half chair, okay? And the reason we call it a half chair is that we've essentially, if you think about, you know, the defining elements of the chair as sort of this pucker, let me go back, as this pucker up on the left and this pucker down. If I go back to my half chair, what I've done is flattened out the carbon that was puckered down. So what's kind of left is half a chair. That sort of makes sense, okay? And I spend a second on this because I want you to see, let me see if I can show it. Yeah, show it reasonably well. So in the half chair, there's 5 atoms that they aren't perfectly coplanar, but they're close. So here, 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 and the carbon in the back, okay? And so this may show it a little bit better. If you imagine that this carbon in the front left, the next one over, the next one, and the one sort of hidden in the back there are just about coplanar. Okay, it's not perfect, but we can just think about it as being in a plane. And then this carbon is sticking up. Okay, it's still out of plane. All right, and so that's why we sort of call it a half chair. And just to, to connect this back, let me just go back to the beginning here. Okay, so this carbon is sort of above that sort of pseudo plane. The plane is right here with the 4 carbon atoms sort of in the middle. What we're doing is we're bringing this end one, we're bringing C1 up into that plane, and C4 is kind of still sitting above the plane, okay? All right, so we get up to there. That's a maximum, and let's let it continue. Okay, so in going from that maximum, from that half chair to this local minimum, I'm continuing to bring C1 up. So the movement is really still in C1. Let me, okay. And this is a local minimum, and this conformer we went through in the recorded lecture. This is what's known as the twist boat, okay? And so I have a little, there's a little bit of maneuvering here so you can maybe see it. Okay. And so, yeah, so hopefully this helps. In the boat conformation, these 2 end carbons would be pointing closer to each other. And the CC bonds in the front here and in the back would be parallel. And in the twist boat, they're just kind of, it's exactly twisted. They're not parallel, they're out of plane. And what that allows these sort of the end carbons to do is to reduce their transannular interactions. So in the Friday lecture, I talked about a flagpole interaction, which is this interaction across a boat cyclohexane between 2 hydrogens. That would involve this hydrogen here and this one here. If I were to force this into a perfect boat, those 2 would come closer together. The twist boat allows them to spread out and lose a little bit of that destabilizing interaction. Okay. And then, because of the symmetry of the molecule, what follows is sort of the reflection of what we just saw. So we just brought C1 on the right all the way up. Now we're going to take C4 and start to bring that down. As I bring it down, I'm going to approach another half chair and then hit a half chair and then ultimately get back to get to my new chair. So here we go. Okay, so I'm bringing down C4. You can see, hopefully from this representation, that I've got, it's not a perfect plane, but I've got 1, 2, 3, 4, 5 carbon atoms that are close to coplanar. And then that one that I brought up, C1, is sticking above the plane. So this is a second half chair conformation that the ring passes through en route to the other chair. And then, just give you a little bit of a look at it. There it is. And then here we go. We're coming down, okay? And so we bring that end carbon down, C4, and we get to this, to the other chair, okay? So your book, unfortunately, does not do a great job covering this, okay? And so I'm going to post this video in the media library, and I'd encourage you just to watch it, and it's very difficult. There's a lot, moving, and it's totally new in terms of the type of movement. So like, it's going to take you guys some time to internalize it, but it's important that, the book always draws like 1 up, 1 down. It's really kind of like 1 up and then 1 down. It's not really a synchronous, movement, as you can see from this energy diagram. So you drag one carbon up, you make a half chair, you keep dragging, you hit the twist boat, and then you start to pull the other one down, you hit a half chair, and then you hit the other chair. Okay. And so let me stop sharing, and I'll see if I can get that whiteboard back. Oh, nice. Okay. We still got them, I think. Let's see if it's here. No. All right. Need to redraw it quickly. So I'm just going to redraw the energy diagram that we had. Okay, so we're talking about cyclohexane itself. So there's no substituents. And in that case, then, of course, the two conformers are equal in energy. So I tried to put them at the same vertical height. All right. And so my pathway is going to look exactly like what we saw in the Spartan video. I'm going to go up. I'm going to have a maximum that'll be a half chair. And then I'll go down. And then I'll go down. And of course, you know, the widths of these peaks and valleys should all be symmetrical. And so here we're pulling C1 up. And so I get to this type of structure. Let me just put in the rest of the numbers. So basically 5 Okay, so I'm bringing one up, and then sort of the 5, 6, 1, 2, 3 are almost coplanar. C4 is above that plane. Okay, and then I keep moving one up, and I get to my twist boat. Okay, and then I start pulling C4 down, and you know, when I pull about halfway, I'm going to get to that half chair. Okay, and again, sort of 2 through 6 here are almost coplanar. And then we keep pushing 4 down, and it drops below the plane of 3, 4, 5, of 2, 3, 5, 6. And I get to the chair conformation, okay? And I would reverse that process to flip it back. So to flip it back, you would start pushing 4 up or 1 down, and then move across the potential energy surface. So I'm going to open it up to questions there, because I know that that's a lot to take down. No questions? told you guys last week that we had 7 chickens, and now we have 2. And yeah, Dad forgot to close the coop on Saturday, and I woke up on Sunday and there were piles of feathers all over the yard, and 5 of them got taken by coyotes. But this is why chickens are $6 a piece. You just go and you replace them. And so we're going to restart the flock here and try to remember to close the coop. All right. So cyclohexane's easy because all of the 2 chair conformations are identical. There's this symmetry. It's very nice to talk about. The more interesting and more common scenario is when you have substituents on the ring, right? And let's just consider, for example, methyl cyclohexane. So okay, so I've drawn methyl cyclohexane with the methyl group in an equatorial position, okay? And based on what we just learned, we know that this can chair flip. And if I do the chair flip, if you forget about the conformational analysis. If you just say, okay, what does the chair flipped conformer look like? Well, all I need to know is that all of the equatorial substituents are going to move to axial positions, and all of the axial substituents are going to move to equatorial positions, right? And so we're sort of digressing to like how you draw these structures. So there's 2 quick little aside here. So there's 2 ways to draw the chair flip structure. One is to go through what we did here, where in the energy diagram, where I pushed one carbon up, pushed one up on the end, and pulled one down on the other end. And so I'm going to draw it that way first, and then I just want to show you guys another way. So again, let me number 1 and 4, 4 and 1. The methyl group is now axial. The hydrogen is equatorial. Okay. So that's you want to be able to do this. So you want to be able to draw the chair sort of in with both, from both sides or both chair conformers. So here, I've got the carbon on the left is up. Here, the carbon on the left is down. Here, the one on the right is down. Here, the one on the right is up. Okay. You want to be able to get comfortable drawing both of those chairs, and just like your hand did, one will probably be easier than the other, but try to figure out how to draw them both. And then just remember that everything that, that the axial equatorial positions change. And so the methyl group was equatorial here on the left, and now it's axial on the right. Okay. And if you aren't coming to that conclusion, there's something funny about your chair. Your chair maybe is not redrawn correctly, or you haven't, perfectly, the bond angles are probably not where they need to be. Okay. So that's like, I'd love for everyone to get comfortable doing that. Okay. And you really should, that should be the goal. There's another way that people will show a chair flip, which I think comes up in some of the problems. So I just want to cover it, which is that you can move the substituents by one position in your diagram. So another way of showing the chair flip for methyl cyclohexane is to redraw the ring with the same position. So I'm not changing anything, but then move the substituents over. So now the methyl group is over here and it's axial, and the H is there. So oops. So of course, in reality, these two are the same. The difference here is sort of how I'm showing it on paper, how we choose to represent it, okay? And so if you imagine taking, yeah, give me one sec, Caroline. If you imagine taking this conformer on the right and sort of spinning it down, you would move that methyl group, you know, kind of in front of you, okay? That is the same as just moving the substituents in the representation by one unit, all right? So there are different ways to do this. This way on the left is sort of the best way if you can get comfortable with it. This way on the right, you're gonna see occasionally used too. Okay, go ahead, Caroline.
Can you move it like, I saw that you moved it to the left. Can you move it like up or to the right, if that makes sense?
Yeah, you can go in either direction. Yeah.
Okay.
Yeah, and that's fine. And that would give you, you know, let's draw it because that's a good one. That would give me, oops. So keeping the chair where it is, move that up there. That would give me that type of representation, which, you know, in fact, looks really close to what we see on in the first one, right? It's a little bit different, but then you can see if you could rotate that, it's equivalent to the one that I drew on the left. So either one of those is absolutely fine. Okay.
Thanks.
Yeah. All right. So so what's cool about this, and this is like, you know, it's really interesting stuff, I think. So these two conformers with methyl cyclohexane are not equal in energy. Okay, so we said the delta G up here for cyclohexane is 0 because I've got all hydrogen substituents. But I think you can appreciate that these two conformers, things are different because here my methyl group is equatorial, here the methyl group is axial, okay? And as it turns out, the axial orientation of a methyl group in cyclohexane is less stable. And less stable, the delta G is about 1.8 kcals per mole. So it's plus 1.8. If we call this, you know, call this 0, this one is 1.8 kcals per mole higher in energy, okay? And so this is getting crowded, so I'm just gonna move to another slide here. So axial methyl, less stable than equatorial methyl, okay? And the question is why? And it's because of what we refer to as a 1,3 diaxial interaction. Okay, so that methyl group, when it's in the axial conformation, we say that there's a non-bonded interaction between the other hydrogens that are in the axial orientation, okay? And that 1,3, that total interaction is worth about 1.8 kcals per mole. Each individual 1,3 diaxial interaction is worth about 0.9. So okay. And so you know, so the reason we use this term is that cyclohexanes are so common. These types of conformational questions come up, you know, every day, and this steric interaction, the 1,3 diaxial interaction, that sort of descriptor makes it easy for us to talk about, what's happening, okay? But in fact, though it may not seem this way, this is not a new steric interaction. A 1,3 diaxial interaction is actually a special type of gauche interaction, okay? And so let me remind you that we say gauche butane, and I'm going to do something here, which hopefully you'll see where I'm going with this. Okay, so this is sort of orientation that we haven't actually, used this type of representation too often. But basically, we're sort of looking along this carbon-carbon bond here, with a little bit of perspective, and so the substituents attached to it are approximately appear approximately 120 degrees, and then these in the front appear to be sort of approximately 120 degrees. This carbon over here on the left is tetrahedral. Perhaps it'd be a little just clearer if I just use a line wedge for that one. Okay. So that is, 1, 2, 3, 4 carbons. That's butane. And if I look down this CC bond, okay, we can generate our Newman projection. And so let me draw what's in the back first, because that'll be a little bit simpler. So my methyl group is up, hydrogen is over, okay? Then we move to our front carbon, so the one over here. Let's do the easy ones first, the 2 hydrogens. One's going down, one's going over into this region, and then I've got my methyl group, okay? And the only difference between this Newman projection and the ones that we've drawn before is that I've drawn out the methyl group. And so I'm just going to stick with that here and draw it out. But typically, if I change that to CH3, you guys have seen that. So hopefully you see that this is gauche butane, right? I have the 2 methyl groups occupying a staggered orientation with respect to each other. That's better than eclipsing them, but it's not as good as moving them further away, right? And so let's work in reverse here. If we go back to this structure and I say, okay, this was, the line structure for this Newman projection. Let me just trace out the carbon skeleton, right? I'm just kind of curious. What does that look like? Okay. And then let's go back one more to cyclohexane. Why don't we just trace the carbon skeleton? What does that look like? Okay. Do you see that they're the same? The relative sort of positions of that 4 carbon unit are identical. Okay. And so if I go and generate a Newman projection for the cyclohexane, looking down that bond, well, it's going to look basically identical to what I have for butane. So I'm going to have in the back a methyl group up, a hydrogen over. Okay, let me put the hydrogens in so you can see them. Okay, so, and why don't we, just to really drive it home, we're going to number atoms. So this is group or number groups 3 and 4. Okay. We've got the ring coming down here. Got my carbon in the front. Here are the 2 hydrogens attached to them, so 3 and 4. And then this methyl group going off to the left is here. And I've got or not methyl group, sorry, ring carbon. Then I got a hydrogen coming up, and then it sort of continues around the ring. And we won't draw the rest of the ring. But compare, right? So they are the same type of interaction. So the 1,3 diaxial interaction is a special type of gauche interaction. It's a gauche interaction in a cyclohexane. So don't let the name confuse you. Okay, and then there's two of them, right? So I only drew one, and I'm only going to draw one, but you should convince yourself that if you look down this bond here in the back that I color in yellow, that you can draw another Newman projection looking down that bond and identify another gauche interaction, okay? And so there are two gauche interactions for each axial CH3, and it's not that they just look similar, they are energetically. So we said butane, a gauche interaction is about 0.9. In methyl cyclohexane, the axial conformer is less stable by 1.8 kcal per mole. That's 2 gauche interactions. Okay? Do you see it? Do you at least, I don't expect this to just come across as like, yeah, I got it. I hope you're following the logic though, and I hope that you'll review the videos and the Spartan video and practice this so you can see it. It's a lot to take down in a very short period of time, but it's not as new as it may look. It's a conformational analysis, and we're basically drawing a fancy gauche butane in a tuxedo. Okay, Christine asks, where's the second gauche interaction? So the second one is looking down this carbon-carbon bond in yellow, okay? So I'm not gonna draw it out. I'd encourage you to do it on your own and try and, work out the kinks so you can draw it out. But you will see that there is a gauche interaction between this methyl group and this other axial hydrogen, just as there's a gauche interaction in the first thing that I drew over here on the right, okay? So again, give it a solid effort. Try to redraw it. If you can't draw it, come to office hour, come to your TA. We can happy to go through it. Don't want to go through it because we're just short on time in class here. All right. All right. So as I said, the more common case is when you have these substituents and this axial position, these axial orientations of the substituents lead to these gauche interactions, which we call, just for cyclohexane, you have a specific name, a 1,3 diaxial interaction, because that helps us to sort of reminds us that it's between the axial substituents in the cyclohexane. And so we call these A values for axial, all right? The A values are the difference in free energy between the equatorial and the axial conformer, okay? And they're well measured, and we're gonna put a couple of them down. So A values are the energy of the axial conformer minus the energy of the equatorial conformer. And so if we say CH3, ethyl, isopropyl, and then say tert-butyl, we can define an A value, which is, just a special type of delta G, right? Value, and it's 1.8, 1.8, 1.9, and then 5, okay? And so we're gonna end with this, and we'll try to finish everything later on for the recorded lecture. But so the A values are the difference in free energy between the axial and the equatorial conformer. All right, it's just a delta G. So again, not a new it's not a new concept. It's the difference in free energy between the things on either side of that equation. In this case, the equation is the conformational interconversion between equatorial and axial positions. And we just like to use the A value term because it helps us to reminds us that it's in cyclohexane, and this is very common. Yeah, Muriel, do you have a question?
Yeah, wouldn't the delta G depend on the other substituents though, or you just assume it's all hydrogen?
Yeah, so yeah, it does. And this discussion is all high. This is all mono-substituted cyclohexane.
Okay.
Yeah, and we'll cover that. We're going to cover di-substituted in the next lecture now. And it gets, as you might imagine, it gets a little more complicated more quickly. But for now, we're just talking about one substituent. And so I just want to end by pointing out something curious here, right? So wait a minute. Methyl ethyl isopropyl are almost about the same. Huh. That may not be what you would have expected from intuition. Ethyl is bigger and certainly isopropyl is bigger. And then there's a big jump when you go to tert butyl. You go from about 2 to 5. So what the heck is going on, right? And this is where, we could arrive at this through a Newman projection, but it's easier to think about it from the sort of the 1,3 diaxial perspective. Let's put the hydrogens in. And let's put my axial substituent there. And I'm going to draw this carbon now with stereochemistry. Okay, so I'm deliberately, let me do a better job of drawing that carbon with stereochemistry. I'm deliberately not showing any of the substituents at the ends of these lines and wedges, okay? But I want you to consider, if I had methyl, it would be H, 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 right? And if I had ethyl, I basically replaced one of those hydrogens with methyl, and I can put it anywhere I want, but where I'm going to want to put it is sort of either here or here. These are the two positions kind of pointing away from the ring, right? And so if I go to ethyl, I'll arbitrarily place it in the back. Okay. And then we can play the same game with isopropyl. So I'm going to keep the isopropyl on the hashes and wedges because those two positions are away from the ring. Okay. And so what I hope you can see is that for each of these three substituents, methyl, ethyl, isopropyl, you can gear them in such a way that you have a hydrogen pointing over the ring or pointing towards those bad 1,3 diaxial interactions or positions, right? But as soon as I go to tert butyl, I lose that option. And now, no matter what I do, I've got a methyl group pointing over the ring. And that is very bad. And so what we say is that for methyl, ethyl, isopropyl, or really for ethyl and isopropyl, you can orient them in such a way that as far as the A13 interaction is concerned, it's essentially the same as a methyl group because you can still put a hydrogen over the ring, okay? But when you get up to tert butyl, you lose all your hydrogen substituents, and so everything's methyl, and so you just have to have a lot of steric crowding over the ring, putting a methyl group in that position. And so that's why you get the big jump from about 2 to 5. And that's why the first three are essentially equal, okay? So, excuse me. So there's a lot to think about in this lecture, I know. Hopefully you find it very interesting. I think, conformational analysis is one of these things that we just love to talk about. And if you can understand these issues, well, I mean, you can draw a molecule and say, okay, I think this is the lowest conformation, or I think that's the lowest conformation, and this is why, So try to work through this lecture diligently, but, allow yourself some extra time, and also the last lecture too, allow yourself some extra time, but really try to take the time to nail it. Because we're gonna build on this in the next lecture, and it's going to come up again and again as you go through this course. So all right, I'm going to stop there, take a 5-minute break. Are there any questions before we go to office hours? Anything that might be good for everyone to hear?
If you were to, in theory, rotate the isopropyl or the ethyl, then you would have a larger number. It's just the standard conformation is the kind of rotated.
Nature will find the minimum, because remember the energy to rotate about single bonds is almost nothing. So I can get, in that case, I can get there, and so it'll just put it out over the ring. Yeah.
Okay. Thank you so much.
Yeah. All right, I'll be right back.